given is proper or not, but because at such a low dose, it cannot be so sensitive. Any other question, please?
What kind of DNA damage you observe?
Sir, here you can measure only DNA damage.
No, what is DNA?
Sir, DNA, all DNA damage is here consistent. I am not specially observed any.
Type of DNA damage.
Sir, this DNA damage consists all single strand break, double strand break, everything.
There is no other question. We thank Mrs. Shiva for the presentation. Now I call upon the next presenter, Mr. Ravi Chunkulwar. The title of his presentation is
Good afternoon to audience. Those who have not seen my poster posted outside, I'm just showing it here just for a glance, and now I'll start the presentation. Electron beam. Electron beam is used in medical applications in a wide manner. In all kinds of beam therapy applications, electron beam is used in different energies. To do the QA, audit or dosimetry of the electron beam in medical applications, we use various radiochromic films. These electron beams, narrow beam electron beams, are also used in non-medical applications like commercial industrial irradiation, processing, and research applications. Okay. Now, in that case also, non-medical applications also, I have used the same radiochromic films which are used in medical applications to quantify the various parameters, physical parameters, and dosimetry also. Here, my talk will be limited to only characterization, not for dosimetry. So, this is just applications like the chemistry towards energy materials, health and picosecond pulse radiolysis, free radical chemistry, nanomaterials, water chemistry, finding new materials for sensor, solar energy storage, and so on. What is my objective? Objective is to determine the electron energy. The very interesting thing is that I have determined the electron energy in a research electron beam accelerator using the radiochromic film, and also the beam profile and beam uniformity. I can also go for the dosimetry, but that I will not cover here. This is a typical layout of the research reactor, electron reactor. You can see here this is the linac, and this is a sample holder, and you can view the sample. You can irradiate sample here, and all supported electronics and everything. This is my experimental setup. This is linac exit window. Then this is my radiochromic film. Radiochromic film I have used SD810, B3 and EBD3. This is all radiochromic films which are widely used in medical dosimetry. The beam profile measurement I have done with the LC810 film. The small films 5 by 5 centimeters square at different distances from the accelerator exit window. The accelerator exit window is this. So this is exit window. So I have gone away from the exit window and I have measured the different beam profile. I have used the Epson scanner to scan the films, irradiated films, and I have noted down the change in the color intensity and analyzed using OmniPro IMRT software, which is very popular in the medical applications. Then energy determination. I have used EBT3 3 by 3 centimeters square. Films are irradiated at different depths in aluminum, PMMA and polystyrene, just like PDD. Okay, the percentage dose depth. So I have done in aluminum, PMMA and polystyrene. I can use only one material to determine the electron energy, but I have just for the confirmation I have used 3 materials, among which PMMA and polystyrene are tissue equivalent and aluminum is not. Each exposed film was scanned by the document scanner. It's very simple phenomena. I just want to have a pixel. I don't want to do any dosimetry here. So I just want a pixel on the film, which can be scanned on my document scanner also. And I have taken the pixels and I have plotted for the and the pixel values I have obtained from image software. I have calculated RP, that is the practical range of the electron particle from the attenuation plots, and then I have determined the electron most probable energy of the electron from this practical range using ASTM standard. You can see here the photographs above in the blue, that is SD810 film, radiochromic film. I have allowed the electron beam fall on that at different distances. The distances are down, you can see this is 40 mm, 60 mm, 80 mm, 90 mm, 110 mm away from the exit window of the accelerator. You can see the screenshot of the IMRT Pro software where I have determined the dia of the electron beam, which are increasing as it goes away from the exit window. It is very obvious because as beam go away from the exit window, it will disperse in the atmosphere, so the dia will increase. But my study was to ensure whether it is perfectly uniform, and so you can see the profile here. Again the same profile we do in the medical applications also. In therapy we find out these profiles. Here also I have done the same using the IMRT software. Then you can see at various distances at various distances from the exit window and the beam dia. I have plotted that, and it is well satisfactory and linear. So the beam dia is following the ideal condition of the spreading. You can see here this graph. This is attenuation graph for the measurement of the electron beam energy, the determination of electron beam energy. This is actually PDD graph, but I will call it as attenuation graph. Here you can see there are 3 materials: aluminum, PMA, polystyrene, and then the normalized pixel values, and then absorber thickness in gram per centimeter squares. How I calculated the energy of the electron beam? You can see the equations given in the ISO ASTM standard. These are the range equations, energy range equations, and observed values from the profile.
Mr. Madhu, you are requested to conclude.
Yeah, just this is the last but one slide. So observed range of the electron particle is, I have observed this, and from putting into the equation I have got energy E, that is 6.66 MeV in polystyrene, 6.995 MeV in PMA, and 7.8 MeV aluminum, which is very much in agreement with the 7 MeV electron beam. It is from the figures it is observed that the beam spot maintains circular shape in various distances. The contours of the isotope plots indicate area over the film, very good uniformity, reasonably good, and attenuation curves which gives the energies determined using the ISO empirical formulas, very much agreeable to the expected energies. Then it is concluded from this work that the determination of the most practical energy of electron beam in tissue equivalent material gives a excellent result. Thank you very much.
One question, please, from the board of the house. A single question. Thank you, Mr. Reddy.
Okay, thank you.
We will move on to the next speaker. Mr. Rajnikant. Dr. C.S. Sureka, please.
Myself, C.S. Sureka from Bharatiya University, Coimbatore. First of all, I would like to thank the organizers to give me an opportunity to present our paper entitled Evaluation of Americium Beryllium Neutron Source Installation using Gen 4 Monte Carlo Code. Prior to installation of any radioactive source, it is mandatory to analyze the suitability of room on safety point of view. Since we are getting americium beryllium source, we are going to get it, americium beryllium source, this study is targeted to investigate the americium beryllium source room using Gen 4 Monte Carlo code. So to do so, it is targeted to design a source drum, that is a source container, using some heterogeneous material, and dose rate evaluations were carried out immediate vicinity of the source drum. So here we are going to use americium beryllium source of activity 16 curie, which neutron flux is in the order of 40 million neutrons per second. Then the source dimensions are 2.2 centimeter in diameter and 7.7 centimeter in length. So this source is simulated using this Gen 4 geometry and tracking Monte Carlo code 4.10. So this Gen 4 Monte Carlo code is an open access code. Moreover, it is very well suitable to simulate more than 100 type of ionizing radiations such as neutrons, photons, most of the charged particles. So this is the very highlighted point of using Gen 4 Monte Carlo code for our application. Then here in this case, we kept this americium beryllium, we have planned to keep this americium beryllium source inside the source container, which is kept inside a just brick room of volume given here. So that's the reason we have planned to make a suitable source container, since the room is not a very fitted one for our application. Then so to make this source drum, we have chosen heterogeneous materials such as bags and high density polyethylene because of their cross section to absorb this neutron, as well as their cross section to produce a very lesser amount of gamma radiation. So the center figure shows the Monte Carlo modeled geometry of americium beryllium neutron source. Then the first figure shows the location of the source drum in the room. So there, inside the box, we would see this wax container in yellow line. Then other layer is high density polyethylene. So inside this source drum, we